right? That's just a phase, all right? Times A times the neutrino, the electron neutrino, plus B times the muon neutrino. Right? My original basis. Okay. So let me just show you what happens to this phase. So now what matters when I go to do a measurement? Like what do we pull, what can we pull out of this wave function?
You pull out the phase, it doesn't really matter. You're going to be able to adjust.
Okay, what matters are things squared. Right? So what we really want is a squared and b squared. Right? Where a squared will tell us that if we measure this thing, it'll be the probability of essentially finding it as a electron neutrino. And b squared will be
a muon neutrino.
All right. Now, if I multiply this arbitrary proof, if I multiply a by this phase, but then squared it, what would happen to this phase? When I complex conjugate it, it goes away. So what happens, this is an idea that he doesn't emphasize here, and I'm doing it here because I just saw it now, it's a nice place to talk about it, is that whenever you solve for a wave function, you essentially pull out this e to the I stuff, which is a phase, and then what happens to that, it's a common phase to both of these things, to both of these projections, and what happens to that common phase? It goes away. All right, and what it really does is it tells you something pretty deep about quantum mechanics, and it's the idea that there's no such thing as an absolute phase. Like, who's to say where a wave actually began? It's kind of like there's no perfect x0, no perfect t0. Who's to say what is x0? Who's to say what is t0? What happens in quantum mechanics is you pull out all the common phase, and who can say what that is? But what you're left with when you pull out the common phase is that whatever thing is here and whatever thing is here represents the phase, the relative phases between these two waves.
So in this case, it would be the cosine and the sine.
That's right. All right. So look, the quantum mechanics, what we're doing when we're doing superposition, and we have a number like an or a or b, those can be complex. And what it means is that one starts here and then the other starts with a phase relative to it. But what we always do is we pull out as much of the phase that's common to both as we can, and that leaves this one, you know, maybe this, so right now, this, let's look at this as without the phase, and this one has the phase. When we pull out this common phase, this is kind of like where we start. And then this one is I, which is what, pi over 2?
Yes.
Pi over 2 away from here. So this is pi over 2 relative phase from here. But what happens to the common phase to both of those? It doesn't matter because quantum physics doesn't care about that.
Cosine and sine are pi over 2 different, so it's fine.
Okay, yeah, I realize that, yeah. But I was trying to just extract this.
Well, multiplying sine by pi over 2 gives you back cosine, so it's...
Yes. All right. Okay. So look, this is a fantastic solution. Look at what you just did. All right. Now, what is very interesting about this problem is, you know, we might be worried about neutrino oscillations, right? So there's this Hamiltonian out there that causes a neutrino oscillation. And so what you want to study is how often does the electron neutrino oscillate into the muon neutrino, because what was the initial state that we started out on?
1, 0.
And what is a 1, 0?
An electron neutrino.
Electron neutrino. And so the question is, does the electron neutrino change into a muon neutrino? All right, and what's the answer?
Yes.
Sometimes.
Okay, so how am I going to express that answer? So how can I express this answer to reflect that cool question?
Doesn't a muon change into an electron?
Yeah, a muon can decay. This is different.
Did you say yes to that because we started off, it was psi general was just in
Okay, so
electron neutrino state, because it was side channels just an electron neutrino. So
Right,
nothing
and
else.
then we
So
solve for
then
what
we
happens
solve
to
it,
that as a
and then
function of time.
We're getting A squared would be a probability of it being in that state, and B squared would be a probability.
That's
So
right.
It
it's
could be either or.
essentially gone into, it could be either or.
Right, and if B were equal to 0,
Is it because you operated the Hamiltonian on it?
yeah, so there's a Hamiltonian that exists between those two things. All right.
The observable that the Hamiltonian produces is a probability A squared that it could be electron neutrino.
So let's
or
plot
B
that. So
squared.
let's do that. Let's plot versus time. Let's plot A squared and B squared. So this is probability for electron neutrino. This is probability of a mu1 neutrino. So what does it look like? How am I going to plot this? What's the answer? I've got it over there. Go ahead, tell me.
1 to 0.
I'm plotting it. I'm going to plot it as a function of time.
Cosine squared.
So cosine squared, what does cosine squared look like?
Even. Starts at 0. I mean, it starts at 1 at 0.
Right, so maybe it looks like this. This is cosine squared, this is A squared. This is the electron neutrino. And what is the other one?
Starts at 0 at
0
0.
goes up to 1.
Right, what happens to the relative phase I?
Changes back to the same.
What happens to, so what happens for the probability to that relative phase?
It's going to disappear.
It disappears, right?
It's squared.
Right, so
Right,
let's see.
yeah, negative
so,
I
yeah.
squared is
That keeps
one.
it real.
So you're right,
That
okay?
keeps it real.
It keeps it real. Alright, and then, so if Matt had to plot it, it would look like this. And what's this? This is B squared. This is like when you're going to be a mu1. So you just did your first legitimate problem. Right?
So sometimes, there's times where it's always going to be a,
Well,
Either
it's here. It's all electron neutrino.
and as it goes down, it could be, it's
It's a
a
superposition.
superposition, and then when it gets to the bottom, it's always,
Yep. All right, but let's review once again our final answer. So,
When it's a half, it could superimpose, it could be either or, but
yeah,
The
you have
probabilities-
such a probability of getting it, wherever, however it probably goes.
So when the two graphs intersect, the probabilities of being either electron neutrino or mu neutrino are equal.
Yeah. So look at what this wave function tells us. We've got this total wave function, it's a function of time. This is how much of it is electron, this is how much of it is a mu neutrino. This is a wave, it's a cosine. And what quantum mechanics says is that this is a cosine wave, and to the cosine wave, I gotta add to it a sine wave. But do I add the sine wave in phase with the cosine?
no.
No, I have to add, so that's my phase. So the complex part of it comes in and showing you where that phase is. But does that have anything to do with the probability?
No.
No, because that goes away. All right, and then don't forget what I also put out of all this thing was a phase that was common to both of those things. And what happens to that thing?
that goes away with
It goes away. And what it fundamentally says is the quantum mechanics can't tell you whether or not there's an absolute phase or not. Well, it says there is no absolute phase, sorry.
there's no absolute point of reference.
There's like no absolute x0, no absolute t0. It's a fundamental symmetry. Right?
It's all relative. The phase
Yeah.
is relative to where you measure it.
Yeah, so this part is relative to, whichever one you decide to call start. I decide to call the electron neutrino start, and therefore the other things are relative to it. So I can't underemphasize how important this problem is. All right, this problem is your prototype problem for neutrino oscillations. It's your prototype problem for electron oscillation, spin oscillation, spins from up and down. It's your prototype for a two-state excitation in an atom. All right, any place where you have two states, guess what? You're going to see. You're going to see this type of thing. And what differs is the Hamiltonian. All right. So like I said at Yale, we're doing this, I wish I could write the Hamiltonian. It's a two-state problem, and I think it's, I think the Hamiltonian is 0, and then delta, and then minus IH, and then, what does this have to be, plus IH?
Yes.
Something like that. So that's how we write the Hamiltonian for our Z0 boson transitions and particles.
That's just H squared.
All right. Yeah, so I won't go into it there, but I used to have the poster up and then they tore it down this summer. And if you go and you look on a poster, whammo, we say, here's the Hamiltonian we're working with, we've got to solve it, find its function time, do all this stuff. So this is a real deal problem.
And the minus I is always, it's always pi over 2? Is that?
No, that's just for this case that came out to be that way.
I
Okay?
thought that was going back to like the e to the I is the same as e to the pi over 2.
Yes, minus I is, oh, sorry, minus I is minus e to the pi over 2.
Minus I
Yeah.
equals e to the minus.
Pi over 2. Or you could say it's plus e to the pi over 3 pi over 2.
Which also equals e to the
Minus 1. Yeah, so
plus
minus 1
3
equals,
pi over 2.
yeah. So minus I equals e to the 3 pi over 2,
Which equals e to the minus pi over 2.
which equals e to the minus pi over 2, which equals minus e to the pi over 2. Right, all those things are equal. But essentially, if you're leaving the minus out in front of something, that's a phase, right? So now you see subtraction is actually a phase difference. It's 180 degrees out of phase. A minus 1 is e to the pi. Right?
It's just not right.
It's wrong, right, Matt?
It's not right.
Well, it's
Well,
probably
it's
not
not
right.
wrong.
It's
It's
not
not wrong.
getting it.
It's not
but
right.
You don't like it because you're getting it. All right, so that was great. And so I encourage you guys to try doing this problem. Again, 2 by 2 I expect you to do by hand. But I would do this problem if I were you using maxima. So what I did is I did the 12 maxima. I input the Hamiltonian, asked it to solve for the eigenvalues, asked it to solve for the eigenvectors, and then I made a plot of the ANs and the BNs. And it looks nice and pretty. Okay?
Is that posted somewhere on
I didn't post it, but if you remind me, I'll post it, all right? So if I don't get it up on Webhost or something like that, remind me, I'll put it up there. Okay, so we're going to now skip to, well, we finished that chapter, all right? And now we're going to go and finish up chapter 4. This problem took way longer to redo. I didn't expect to do this at all, although I wanted to have some. I admit, we got to some nice discussions I wasn't even planning on. So that was cool. But let's go and try to finish up chapter 4. And then we have the test next Tuesday. And on Thursday and next Thursday, we'll be working in chapter 5 and getting as much as we can.